Ever wondered how AI decides what qualifies as hate speech, and why it so often gets it completely wrong? Take this example. A slur targeting one group might trigger a 98% hate speech flag, while the exact same slur aimed at another group slips through the cracks. Today, we're diving into a groundbreaking study that's reshaping how AI detects bias, with a focus on the Dutch language. Let's unpack this critical work. Here's the core issue. Hate speech detection models act as digital watchdogs, scanning text for harmful content. But here's the problem, they're not neutral. Consider two sentences. All Moroccans are troublemakers and all Dutch are troublemakers. If the first is labeled 98% hateful and the second only 10%, the model isn't just wrong, it's reinforcing real-world inequities. This bias isn't accidental, it's baked into the data these systems learn from. The study tackles this by asking a deceptively simple question. What if we tested whether a model's decision would change if we swapped a sensitive detail, like a person's nationality or ethnicity? Think of it as a linguistic stress test. If a model flags one sentence as hateful but not the other, it's biased. The goal? To train AI to treat all groups equally, regardless of context. But how do you test this? Researchers created counterfactual sentences, rewritten versions of real posts where social group terms like Moroccan or Dutch are swapped. For instance, that Turk is lazy becomes that Belgian is lazy. If the model flags both as hateful, it's fair. If not, it's biased. The challenge: Dutch grammar is notoriously complex. Swapping young for female in a sentence might sound unnatural, but the AI must learn what feels right. The team tested 3 methods to generate these counterfactuals. 1. SLL sentence log likelihood, a math-driven approach that predicts grammatically natural swaps. It generated 49,000 examples, but occasionally missed cultural nuances, like swapping young for female in a way that felt forced. 2. MGS manual group substitution, a rule-based method that only swapped nouns with nouns. It avoided grammar errors but sometimes lost nuance, e.g., turning speak Dutch into speak Turkish, which didn't fit the original context. 3. LLM-based methods. Advanced language models generated smoother swaps but risked introducing new biases. For example, flipping discredit to glorify simply because a term was flagged. The winners? SLL. It produced more balanced, contextually accurate counterfactuals, reducing biases in how different groups were treated. For instance, other methods sometimes turned Moroccan brothers into Moroccan person brothers, a nonsensical phrase SLL avoided. But here's the catch, even SLL isn't perfect. While it improved fairness for most groups, it accidentally amplified biases in the toxic class, like overflagging or underflagging harmful content. This highlights a key truth: fairness in AI is a delicate balancing act. Why does this matter? If we don't address these biases, AI could unfairly silence marginalized communities or let harmful content thrive. This research isn't just about fixing algorithms, it's about ensuring technology reflects the equity we strive for in society. The road to fair AI is long, but studies like this are lighting the way. Thanks for watching. If you want to explore how these techniques apply to other languages or dive deeper into the math behind SLL, hit subscribe. The future of AI depends on questions like these, and now you're part of the conversation.